you see anything? Plug it in from here. Does it make any difference? Do you see anything?
No.
Okay, I've got no clue.
Maybe it's a problem with the iPad. Maybe you can close it and open it.
Yeah, try that as well. Let's see. I can close that.
Sorry, I can't make a phone call with your iPad.
I want you to make a phone call as well. Let's see. I turn it off. I don't know how to turn it off really. No, not showing.
מאוד מוזר, לא רואים. לא רואים.
No. Okay, so here's what I'm going to do. Since I can't seem to be able to make it work right now, what I will do in order to do a screen mirroring. Okay, it's not working, so I don't know why. So here's what I'm going to do. I'm going to upload my lecture notes from which I'm taking the less okay. It's not going to be as good, but it will be. So let's do the. I'm going to share the screen. This screen, I think. All right. Do you see now my? Do you see now the lecture notes I have?
Yes.
Yeah, you do see it. Okay. So it's not as good, but I will go and you see my mouse here, right? So I'll go as good. This is the explanations that I have, and we just go over that so we don't lose the entire time. Okay. And I will explain to you. We'll follow on the main equations. I'll try to do it slowly. The advantage of me talking is that and writing, and that's the reason why I like to do it, is because I do it at the same pace in which you are writing. And if I already wrote things, then I don't know if it takes if I don't go too fast. But let's do it like that for now, so we don't lose this entire lecture on technicalities. So we're talking about killing vectors in maximally symmetric spaces. And what I say that in a maximally symmetric space, the space is homogeneous. So there is a killing vector in every location X. And it is also isotropic, meaning there is also always an infinitesimal isometry. An isometry, to remind you, is a coordinate change, right? That from x mu to x mu prime, which is x mu plus some, k mu times epsilon. Epsilon is an infinitesimal parameter, where k mu is the killing vector, right? The correct way of thinking of that, you had that at home to write down all the killing vectors of Euclidean space, right? So think of rotation, right? The rotation around the x-axis would be minus y and plus z, right? But leaves the x 0. So k lambda of x would be 0, but you'd have all these possible killing vectors, which are subject, of course, to the killing condition, right? That k lambda nu is equal to minus k nu lambda. Right? And of course, as I pointed out here, there are a total of n times n minus 1 over 2 independent such killing vectors. Now, the important point to remember, and that's the derivation that I want to have, is that for this condition of a maximally symmetric space, we have these rotations in which k lambda is equal to 0, but then k lambda derivative with respect to nu is equal to minus k nu derivative with respect to lambda, which is the killing condition. So I use this result in the equation which we derived last time, which is equation 10 here. Right, so you see that on the left-hand side, there is k lambda kappa, and in the right-hand side, there is a k lambda. So I can use this condition with k lambda being equal to 0, and then the anti-symmetric part of k lambda kappa needs to be 0 as well. And so that leaves us with the anti-symmetric coefficient of k lambda kappa. So this part here on the left-hand side is a minus r lambda rho sigma nu delta kappa mu plus r lambda mu sigma nu delta kappa rho minus r lambda sigma rho mu delta kappa nu plus r lambda nu rho mu delta kappa sigma, which is just the coefficient that we had back in the equation that we wrote last time. So this is in fact identical to what's written here. In fact, actually, I can actually write on that. This part, okay, is in fact, if you look at it, this is just exactly. See it? This is just in fact exactly what is written here. Get lost. Disturbing my screen. That's in fact exactly what's written here on the left-hand side. And on the right-hand side, it's exactly the same, but with kappa and lambda interchanged. Right, so we have a minus r kappa rho sigma nu delta lambda mu plus r kappa mu sigma nu delta lambda rho minus r kappa sigma rho mu delta lambda nu plus r kappa nu rho mu delta lambda sigma. Okay, so just write down these coefficients. Now the next step I do is to contract kappa and mu. Now when I'm contracting kappa and mu, right? So the delta just gives us n, right? Because it goes over the n dimensions. So it's a minus n r lambda rho sigma nu. Plus I contract kappa and mu, then I have here r lambda, and then mu is contracted with kappa, and I have a delta kappa rho, so it's just a rho sigma nu. And then a minus, again, kappa and mu are contracted, but then I have a delta kappa nu, so that's a minus r lambda sigma rho nu. And here the same, r lambda nu rho, and then the delta mu kappa sigma, and then the contraction gives us just sigma as the last term. And then on the right hand side, right, we have here contraction of kappa and mu. So again, minus r lambda rho sigma nu is the first term. The second term is 0 because I'm contracting kappa and mu, right? And when I have a Riemann tensor with the first two indices the same, right, I can exchange them and I get the minus sign. So this second term is 0. So that gets away. I'm actually right. That's not. That lost. What can we do? That cannot do either. So I guess the only thing I can do is just highlight things, right? So the second term here is 0. The third term, right? I have a minus r. So I exchange the two, the rho and mu. So I have a minus r sigma mu rho, and then I contract the kappa and mu. So I have a minus r kappa sigma rho kappa, which is just r sigma rho. So I end up with the third term with a minus sign r sigma rho, and then the delta lambda nu. And the same happened with the last term. So again, I switch the order of the two indices. I end up a minus sign, and I contract. So from the Riemann, I get the Ricci tensor. So I ended up with a minus r nu rho delta lambda sigma. Okay, not too bad. Now, okay. Then the next step to do is to use the cyclic sum rule to get rid of all these last three terms, which end up to be 0. And multiply by g lambda alpha with lower indices. So I take this equation, right? These three guys here are removed, so they're 0. I multiply by g lambda alpha, and then I just switch the order. I mean, this term here I just take to the right-hand side, and these two terms I take to the other side. So I end up with an n times r. Since I multiplied by g lambda alpha, then it's an n times r alpha rho sigma nu, and here I have a minus 1 r alpha rho sigma nu. That's the n minus 1. And then these two terms are just these terms move to the other side. So a minus will turn into a plus, so it's r nu rho. And then I have a delta sigma lambda times g lambda alpha, so that's g alpha sigma. And then this term here is a minus r sigma rho g alpha nu. All right, so I just remove these three terms here. This term I moved to the left, to the right, and these two terms I moved to the left, and I ended up with this equation, which I mark as 13. Yeah? You're with me despite this kind of non-standard way of writing. Okay. Now I use the symmetry. Actually, this is wrong here, so forget about it. I use the symmetry between alpha and rho, right? So when I switch alpha and rho, I get a minus sign, right? So I have R nu rho G alpha sigma minus R sigma rho G alpha nu, right? This part here is just written here. And then when I switch the orders, I should get the minus sign. When I switch the order of alpha and rho, forget now about the sigma and mu. When I switch the order of alpha and rho, right, then I'll have a minus R nu alpha G rho sigma, right? I switch the alpha and rho, and then a plus R sigma alpha G rho nu. Again, I switch the order of rho and sigma. And I use the fact that the Riemann tensor, when I switch the first two indices, it gets a minus sign. Yeah? Okay, then the next step is to multiply by G alpha lambda with upper indices and contract lambda and nu. So when I do that, right, I multiply by G alpha lambda. So I have a G alpha lambda, G alpha sigma. So I ended up with delta lambda sigma. Right, yeah. So I have an R sigma rho. Wait, no, sorry, I did something wrong here. Sorry, no, fine. I contracted with the lambda and nu, so that's okay. So I ended up with R sigma rho. Then here I have G alpha lambda, G alpha nu, so that gives me a delta lambda nu. When I contract with a lambda and nu, that I get an n, right, with the dimensions. So that's a minus n times R sigma rho. And then on the right-hand side, I have a G alpha lambda R nu alpha. Then that will end up with an R lambda nu, but then I contract, so it's just a minus R lambda lambda times G sigma rho. And then the last term again is R sigma sigma alpha times G alpha lambda. So again, contracting with lambda and nu, then it will be a delta alpha rho. So I end up with an R rho sigma. Yeah. Okay. Which means that I can take all that, right, and use the symmetry of the Ricci tensor, right? So R sigma rho is R rho sigma. So I ended up that R sigma rho is just, you know, the minus and the minus cancel. So it's just 1 over n G sigma rho R lambda lambda. Again, this is a property that I end up from a maximally symmetric space. Okay, so far you with me? You managed to follow? Yeah? We're nearly there. So after I wrote that, R sigma rho, I can simply use that back in this equation here to write down, ended up with equation which I call 17, R lambda rho sigma nu, right, is just Every time I have in R sigma rho, I just replace with a G sigma rho times R lambda lambda divided by N. So this is just R alpha alpha, right? It's just a dummy index divided by N times N minus 1 times G nu rho G lambda sigma minus G sigma rho G lambda nu. Right? What I did here, I just replaced the alpha in equation 13. Right? I replaced the alpha with a lambda. So every time there is an alpha here, there is a lambda because I wanted to keep the alpha for the dummy index for the Ricci tensor. Right, so I had an R nu rho. So every time there was a sigma, I replaced it with a nu. So that's why I got the G nu rho here. And the G lambda sigma is just the G alpha sigma that is here when the alpha was switched into a lambda.
The R alpha alpha could be written as the Ricci scalar.
Sorry, yeah, it is the Ricci scalar. I could simply write it as R. I prefer to use R alpha alpha. At the moment, I cannot even tell you why I did not simply write it as an R. Actually, I'll show you that in a second. You know why I did. Okay, and the same for the second term, which simply follow from the second term in this equation 13. Okay, so we're nearly there. So in a maximally symmetric space, we found a simple way of writing the Riemann tensor, right, as the Ricci scalar multiply by this multiplication of these metric tensors. Of course, this is only true in a maximally symmetric space. Now, the last thing that I want to do, I told you there are like 10 equations, not too many, right, is to use the Bianchi identity, which we derived, and is written here. Nabla mu of R mu nu minus 1/2 R G mu nu is equal to 0, right? And combine it with the equation we got for R mu nu or R sigma rho that we derived up here as 1 over N G sigma rho times R lambda lambda, right? So I use G to, so again, rather than mu and nu, I write it down as a sigma and rho, or I can multiply that. Mu is replaced with a rho, and I multiply with a G sigma mu. So I cannot do that because I have nabla mu. So I just replace mu with sigma. So I end up with a 0 is equal R sigma rho minus 1/2 R, which is R lambda lambda times delta sigma rho. Covariant derivative with sigma. And now I use this result that we derived up here of R sigma rho as 1 over N G sigma rho R lambda lambda to write this down as 1 over N minus 1/2 R lambda lambda derivative with respect to sigma. And that shows that provided that we are not in a two-dimensional space, in two-dimension that's not going to work, but in any dimension which is larger than 2, right, specifically 3 or 4, which is what we're interested in, that means that R lambda lambda, which is simply the Ricci scalar, needs to be equal to 0. Sorry, since its derivative is 0, it has to be constant in space, right? It sounds very abstract, but you'll see in a moment that what I'm saying actually makes perfect sense. So in a maximally symmetric space, the Ricci scalar is constant. So because it's constant, it's handy to write it down, multiply by n or divide by n times n minus 1 and, call it the curvature constant, which we denote by k. So it's just a constant, it's just a number, right? And we plug this number here since this is a constant and n is the dimension of space which is known. So I simply call it k and I can write down the Riemann tensor for a maximally symmetric space as r lambda rho sigma nu is just some constant, k, times g nu rho g lambda sigma minus g sigma rho g lambda nu. And that's the result that I was up to. That's the result that I wanted to derive. So there's more than one way of deriving this result, of course. In different textbooks, you'll find different ways of deriving it. I did it in a way which I think is the most straightforward. I followed Weinberg, if you want to follow this specific derivative. Okay, so in a maximally symmetric space, again, when you think of a maximally symmetric space, what it will be like a Euclidean space, essentially, right? It's a maximally symmetric space. Then the Riemann tensor obtained this form. Okay, questions? Any questions? No. By the way, is this being recorded? I hope it is. I'm not sure. Anyway.
Yes.
Okay, good. So that's the result that we need to derive the Robertson-Walker metric. So remember this result, we're going to use that. Now, I told you that for the Robertson-Walker metric, so we're now trying to essentially describe the universe. And we said that on a very large scale, the universe is homogeneous and isotropic, but only in the spatial part, not in the time direction. So the universe in the past, it does not look the same like the universe in the future. It is changing with time. This is an observational fact. And so I told you, technically, that means that we are dealing with a space which has a maximally symmetric subspace. In mathematical words, we'd say that we have a space that looks like an R, right? R is the time direction multiplied by sigma. Sigma is this homogeneous and isotropic submanifold. Now I want to remind you that I think it was in the first lecture, or one of the very first lectures, I told you that when we talk about four vectors, we always denote them with Greek indices, mu, nu, alpha, beta, etc. But when we deal with only spatial part, then we denote them with Latin, regular Latin letters, I, J, K, and this is exactly the time where this is taking an effect. So we have a metric which has a homogeneous and isotropic spatial part. So I can write down the metric as ds squared is a minus dt squared plus a square of t, which is a general function which depends on the time, times gij of x dxi dxj. All right, so t is the time or time-like coordinate, and the x1, x2, and x3 are the coordinates representing the spatial part of the universe. Okay, so this is the most general metric that describes the universe where I make a separation. Right now, I didn't yet say anything about the universe being homogeneous and isotropic, but I just say I make a separation between the temporal coordinate or the time-like coordinate and the space-like coordinates. Yeah. Okay. And of course, Gij would be the metric that represents the maximally symmetric metric on this sub-manifold sigma, which represents the space. Now this multiplication factor A of t, well, it has a name. It's called the scale factor. So mathematically, it is what enables the universe to evolve in time. Right? We say that the universe in the past is not the same as the universe in the future, so it can change with time. And AT is exactly what tells us how it changes with time. So this is called the scale factor. And essentially, when you think of it, it tells you like how big the space-like coordinates are as a function of time. We'll get back to that later. Yeah. Another thing is that when I write the coordinates in this way, these are called co-moving coordinates, right? Because all the space-like components of the coordinates are a function of only a single function of time. In other words, there is no cross terms like dt dx here, right? So these are the coordinates that can be put by an observer who is steady with the coordinates, so flowing with the coordinates, essentially. That's what's called co-moving. Now, just out of curiosity, when we observe the universe with telescopes, which is what we do essentially, can we say that we are in a co-moving coordinates? What do you say, guys? Are we in a co-moving coordinates? It's a question to you. What do you say? Anybody? Can you hear me? What do you say, guys? Are we in a co-moving coordinates?
I think we are.
You said that? One
Okay.
person had the courage to speak. Come on, guys.
I guess we aren't.
We aren't. Why do you think we aren't?
Because I think you said we need to be maximally, like we need to be far away to see everything homogeneous and isotropic. So I guess from our place, it's not true.
No, I'm talking about coordinates now. No, so okay, so you missed that point. Co-moving coordinate is something that moves with the flow, right? Basically, you don't see any change in time. Now, in fact, we are not, and the reason is that the Earth rotates around the sun, and the sun is rotating around the Earth, right? So we have a motion with respect to the coordinates, right? So that means that we're not co-moving, right? And where do we see that? For example, when we look at the cosmic microwave background, right, which is the same in all directions, if we look very closely, we are seeing a slight difference, but this difference comes because of the Doppler shift, because we are moving with respect to a constant field of radiation, essentially, right? So so we do see a Doppler shift. So we have to take care, remove this Doppler shift. So we actually can measure the motion of the Earth around the sun using the measurements of the cosmic microwave background radiation. Similarly, we have another component that comes from the motion of the sun around the center of the galaxy. right? You know that the sun itself is also rotating around the center of the galaxy. Finishes a rotation in, I don't know, billions of years, right? So that's why we're not co-moving. Co-moving means that we're not, if we're not moving at all with respect to the coordinates. Yeah? Model that once we remove that, but we know how to compensate for that because we can easily measure the motion of the Earth, right, around the sun. Then we can compensate for that, then we can go back to a co-moving frame. Good. Now, okay, so we're not co-moving. So now, well, we didn't have this mathematical derivative for nothing. We write down this equation that we just derived of the equation of the Riemann tensor in a maximally symmetric space. But now I add up this superscript 3 to represent the fact that we're really talking about only the 3 space, not the 4 space. So Rijkl is just k, right? This constant that we had times Gik Gjl minus Gil Gjk. Right? This is exactly the same equation that was written above here, only with lambda, rho, sigma, and nu now being replaced with I, j, k, and l. That's all. Right, so Rijkl in 3 dimensions is just k times Gik times Gjl minus Gil Gjk. Okay, and the Ricci tensor, right? Now we're talking about 3 dimensions. So we derived it above in here, where r lambda lambda we wrote as n times n minus 1 times k. Then the Ricci tensor, the n and the 1 over n cancel, is just Rjl is n minus 1 times k times Gjl. Where for 3 dimensions, we can simply put in, it's just 2 times k times Gjl. Yeah? Yeah, maybe. Okay. Now, okay, in order to continue the derivation, we said the following. Now we're going to use back what we did for the Schwarzschild metric. Because the logic is that if we say that the universe is a maximally symmetric, then it obviously has to be a spherically symmetric. Right? So isotropic, in other words. And we already make a lot of work on spherically symmetric metrics when we derive the Schwarzschild metric. Then we showed that, when we looked at the spatial part of the Schwarzschild metric, so I write it as T sigma squared, is it just Gij times dxi dxj. We wrote it down as e to the power 2 beta of r times dr squared plus r squared d omega squared, where d omega squared is d theta squared plus sine squared theta d phi squared. Yeah? You remember that. If you don't remember that, then I'll refer you back to the discussion we just completed last time about the Schwarzschild metric. Right. Okay, so now we basically have to repeat back similar things than we did for the Schwarzschild, but fortunately we already did this for the Schwarzschild. So we essentially repeating the same steps which we already derived, right? And we essentially want to calculate the Ricci tensor for this spherically symmetric space-time. And again, following the same steps that we did when we derived the Schwarzschild metric, right? We had this alpha multiply dt and beta multiply dr. So we set alpha equal to 0 and d0 beta equal to 0. Then we end up, again, you can simply look back at what we did there. It's pretty much, not pretty much, it is identical. That now the 3 reminds us that we're doing the 3-dimension. The components of the Ricci tensor R11 in 3 dimensions is just 2 over R d1 beta, so the beta over the R. And then R22 is just e to the power minus 2 beta times R d1 beta minus 1 in parentheses, all that plus 1. And R33 is just R22 multiplied by sine squared theta. Now, as we wrote down, R ij is just 2k g ij, or jl, this is written here. So now what we do, so this is where we take the, so we use again this property from a maximally symmetric space. And we can do it for R11 and R22. So for R11, it's 2 over R dr beta is equal to 2k g11. Right, and g11 from the metric is just e to the power 2 beta of R. So we have 2 over R dr beta is just 2k e to the power 2 beta of R. And then for R22, again, we just plug in this result, e to the power minus 2 beta times R dr beta minus 1 plus 1 is equal to 2k g22, which is just 2k R squared. So we have these 2 equations, which we can, just plug it in here and solve for dr beta, and then we can immediately solve for beta. So that's a very straightforward algebra. Might just use this to dr beta is just 2k, oh, the 2 and 2 cancels out, so it's just rk e to the power 2 beta. Just plug it in here. And you end up that beta is minus 1/2 ln of 1 minus k R squared. And when we plug it in, since we had e to the power 2 beta, that's just great. That just means we have 1 over 1 minus k R squared. And so we end up with a metric that looks like ds squared is minus dt squared plus a squared of t times dr squared divided by 1 minus k R squared plus R squared d omega squared. The omega squared is d theta squared plus sine squared theta d phi squared. Now, this has a name, right? This is the Robertson-Walker metric, or RW. This is the Robertson-Walker metric. This is the metric. Now, okay, the way it's being formed, right? There are 2 functions here which are not fully determined, right? One is this A, the scale factor, and one is K, right? Which we call the curvature constant. And this is the most general metric written in comoving coordinates that describe a space with a maximally symmetric spatial part. Yeah, you all with me? Okay, and one point is that so far we did not even make an attempt to solve Einstein's equation, really, if you look at that. We just looked at, well, no, we did not even try to solve Einstein's equation. We're just looking for spaces which have this maximally symmetric subspace property. I did not use that in Einstein's equation, right? Or G mu nu is equal to T mu nu. Okay. Now, in principle, this constant k, the curvature constant k, can have any value. I did not say what value it has. I just say it's a constant. But in practice, we don't really care because we can always renormalize. Because if you look at that, you see that if I normalize k to k divided by its absolute value, and at the same time I normalize r to r times square root of the absolute value of k, and at the same time I normalize a to a divided by square root of the absolute value of k, then this equation looks exactly the same, right? If I'm normalizing k, I need to also normalize r, right? And then this denominator is not changed. But since I normalized r, I have an r square, I also need to normalize a, which will multiply dr squared here and r squared here. So when I do all this renormalization, then nothing changes, right? So that means that although k can take any value in principle, then physically there are only 3 values of interest for k, right? Which are k equal to -1, k equal to 0, or k equal to +1. Right? Any other value of k, I can simply renormalize the coordinates, r and the scale factor, and just absorb them in there. Yeah? You with me? Yes, no, maybe? Okay.
K equals 0, give you a problem in A if you renormalize it.
No. Well, then I don't need to renormalize it, right? If k is equal to 0, I don't need to do any renormalization.
Oh, right. So I think, right.
Right. Okay. Now these solutions have names. So the k equal -1 means that there is a negative curvature, which is constant, and then such universe is called open. Right. This is a k equal -1 that refers to an open universe. K equals 0. How do we call a universe which has a 0 curvature?
Flat.
Flat, right? This is just a flat universe. If you look very carefully, you see that when k is equal to 0, what is written here is just Euclidean space written in spherical coordinates. Which again makes sense, right? Euclidean space is maximally symmetric. Yeah? K equal to 0, this term disappears, and then I just have dr squared plus r squared d omega squared. This is just Euclidean space, which I wrote in spherical coordinates. And the k equal +1 is corresponding to what's called a positive constant curvature. And then such universe is called closed. Yeah. So these are the three types of universes that one can have in this Robertson Walker metric. Universe can be either flat, can be closed, or can be open. By the way, do any of you know which type of universe we actually live in?
Yes, if it's expanding, it's open.
No, that's not the same thing. It's not the same thing. We'll get back to that.
But Asaf, when you say open and closed, it's like a, you know, an open, I don't know, like an open part of the what?
Okay, let's look at this closely. Let's start with the flat. So flat case is k equal to 0, right? K equal to 0, I just said, right? You can write down the spatial part of the metric, which I denote with a small sigma. D sigma squared is just equal to the r squared, right? K is equal to 0, plus r squared d omega squared, which again is just writing down the Euclidean space, dx squared plus dy squared plus dz squared. So it's a Euclidean space written in spherical coordinates. So it's a simple flat Euclidean space which behaves like R cubed. Right? Now it can be something a little bit more complicated, but forget about that, we don't care. Not here, at least. Okay. Now, for the k equal 1, right, if we put k equal plus 1 here, then here we have dr squared divided by 1 minus r squared. Right? Now, this can be rewritten by changing coordinates yet again and writing down r is equal to sine chi. Right? So if we write r is equal to sine chi, right, then 1 minus r squared is just 1 minus sine square of chi, which is just 1 over cosine square of chi. And dr is just cosine chi d chi, and so the cosine, since we have the r squared and the cosine square in the denominator and in the denominator would cancel out. And we could write down the metric as the spatial part of the metric as d sigma squared is just d chi squared plus sine square chi times d omega squared. Right? Now, what is this metric? What is just described here?
Just a sphere.
This is a sphere. This is a three-dimensional sphere. It's not a two-dimensional sphere, it's a three-dimensional sphere. Now, technically, it has a name, which you may heard the name. It's called De Sitter space. So again, when you think of it, that makes perfect sense. I mean, you know, we're looking for a space which is a fully maximally symmetric, right? So what type of maximally symmetric spaces we can have? Flat space is maximally symmetric, and a sphere is a maximally symmetric, right? An ellipse would not be maximally symmetric, right? Now, the third alternative is for the open universe, where we have a k equal to -1. And here again, the mathematical manipulation is pretty straightforward. Rather than writing r is equal to sine of chi, we can write down r is equal to sine hyperbolicus of chi, of another function, called psi. So R is equal to sine hyperbolicus of psi. And again, you have here when k is equal to -1, right? Then in the denominator, you have a 1 plus r squared. Sine 1 plus sine hyperbolicus squared, just cosine hyperbolicus squared. Again, remember this. And you end up that in that case, this sigma squared is just the psi squared plus sine squared psi d omega squared. Now, this is something which is much more difficult to visualize. If you remember, I tried to visualize you a negative curvature to space as some saddle, right? The reason why it looks like a saddle is if you take two parallel vectors and they go along this space, they will divide away. They will get away from each other. The same way as on a sphere, if you take two vectors and they go along the sphere, they will essentially merge, right? The North Pole, so they get closer together. So in some sense, that's why you can think that a sphere is closed and the saddle is open. Right, so this is a three-dimensional space with a constant negative curvature. Again, it's more difficult to visualize, but this is the general structure of a saddle. And mathematically, the term is called anti-de Sitter space. Okay, so we have a flat space. We have a closed space, which is called the de Sitter space, and we have an open space, which is called an anti-de Sitter space. Yeah? Questions? Any questions? Now, again, what we did so far was to find a solution to a universe which has a maximally symmetric spatial part. And not surprising, what we found is that we have these three options. Maybe, yes, surprising is that these are the only three options that exist. Any other curvature can be simply absorbed into the definition of the coordinates.
So maybe a little unrelated question, but like it's more general, I don't know. How it is connected to Poincare conjunction, like about the shape of the universe? Isn't there some mathematical constraint that how the universe should be? Regardless of the specific metric, if you assume something which is connected.
I do not know the answer to that. I can maybe discuss it later. I do not know.
Okay.
Possibly because I'm not sure that I fully recall what is the Poincare conjunction on the universe.
Yes, I also don't really remember. Just remember that it's like a popular sign, but I do remember that mathematically you can, if you assume something which is simply connected or something like this, if the universe is dead, so you can reduce it to be a sphere or something. This is homomorphic to a sphere.
I do not know, and I cannot comment on something which I do not know. Okay, so these are the three spaces that we can have, which has a maximally symmetric subspace. Now we have to go through again a little bit of somewhat annoying calculation. I'll do that. I'll take a few more minutes because of these technicalities that we had, so I'll end up a few minutes late. Or at least we'll start to do the derivation. It's actually mainly telling you the derivation, but it's quite annoying. But as promised, I'm not skipping any step here. So so far we have the Robertson-Walker metric, and we saw that we can have three different types of metrics based on the values of k: 0, -1, or +1. So That's kind of easy. We still did not say what we can do, what we can say about this scale factor A of t. We just know it's a function of time which multiplies the spatial part of the universe, right? But what function of time is it? So in order to find this function, we actually have to put this metric that we find inside Einstein's field equation and solve Einstein's equation. This is on the one hand annoying, on the other hand it is straightforward. Again, right, so you remember the Einstein's equation, we have the Einstein's tensor, which is composed of the Ricci tensor and the Ricci scalar, which by themselves are composed of the Riemann tensor, which depends on the affine connection, which depends on the metric. But now that we know the metric, it's just a matter of, putting it, just going through the formulas that we derived and writing it all down. So when you write down, I use here A dot to define as the A over the T, and you write down the Christoffel symbols, this is how they look like. So for those of you who copy, let me just say it out slower, right? So of course, these are the non-zero Christoffel symbols. It's gamma 0, 1, gamma 0, 1, 1 is A times A dot divided by 1 minus KR squared. Gamma 0, 2, 2 is just A times A dot times R squared. Gamma 0, 3, 3 is A times A dot times R squared sine squared theta. Gamma 1, 0, 1 is just gamma 1, 1, 0. It's just gamma 2, 0, 2. It's just gamma 2, 2, 0. It's also equal to gamma 3, 0, 3, and gamma 3, 3, 0. And this is simply A dot over A. Gamma 1, 1, 1 is just KR divided by 1 minus KR squared. Gamma 1, 2, 2 is minus R times 1 minus KR squared, and gamma 1, 3, 3 is minus R times 1 minus KR squared times sine squared theta. Gamma 2, 1, 2 is gamma 2, 2, 1 is gamma 3, 1, 3 is gamma 3, 3, 1 is 1 over R. Gamma 2, 3, 3 is just minus sine theta cosine theta. And gamma 3, 2, 3 is equal to gamma 3, 3, 2 is equal to cotangent theta. Okay, anything else here is 0. Now, I do not know if you copy that or you do not copy that. At the same time, I do not know if it's worth asking that in an exam or not. But it's really just, today you can simply ask your favorite program, such as MATLAB or Mathematica or even Python or I don't know what exactly. And you just plug in the metric that we derived, and that's what you get. Okay, after you calculate the Christoffels, then the only non-zero components of the Ricci tensor, I skip a few steps here. Actually, I did not, because the entire Riemann, you can get it right away because of the maximally symmetric spaces. So the non-zero components of the Ricci tensor would be R0, 0 is just minus 3 A dot dot over A, right? A dot dot is the second derivative of A with respect to time. R1, 1 is A times A dot dot plus 2A dot squared plus 2K divided by 1 minus KR squared. Again, K can be either minus 1, 0 or plus 1. R22 is R squared times A dot dot plus 2A dot squared plus 2K. And R33 is R22 times sine squared theta. Yeah? Yeah? Those of you who know or following me? Maybe somebody is following their cell phone, I don't know. Those of you are following me, yeah? And then, plugging all that in, it's pretty straightforward now to calculate the Ricci scalar, which is just 6 over a squared times a dot dot plus a dot squared plus k. So that gives us everything we need on the left-hand side of Einstein's equation. But now, as opposed to what we did in deriving the Schwarzschild metric, the right-hand side is not zero. Right? Because we cannot claim that the universe on a large scale is empty. Right? It contains matter. Right? It contains energy. Now, what can we claim about this matter and energy context of the universe? There is one very strong assumption which I'm going to use. What is that?
Perfect fluid.
Exactly, very good. So I'm assuming that that the matter in the universe can be described like a perfect fluid, right? Again, this is the cosmological principle, essentially, right? Now remember, very long time ago when we discussed special relativity, I actually introduced to you the energy momentum tensor of a perfect fluid. All right, I told you we're going to have to make use of it at a certain point, and this is the point that we have to make use of it. So, a perfect fluid is a fluid that I can argue that it's isotropic in its rest mass, in its rest frame. All right. So for this fluid, we showed that the energy momentum tensor takes the form of T mu nu is equal to P plus rho times U mu U nu plus P times G mu nu, where rho is the energy density, all right? P is the pressure. I don't know how many of you have ever noticed that the pressure and the energy density actually have the same units, right? Again, these are measured in the rest frame of the fluid, right? U mu is the forward velocity of the fluid. Okay, now, if I can treat the fluid as a dust, then what is the pressure of a dust?
Zero.
Zero, right? So, okay, good that you remember. Right? Now, okay, obviously, if the fluid is isotropic in some frame and the metric is isotropic in the frame, then it's the same frame. Right? It's quite obvious. So, in other words, we can say that in a comoving coordinates, which is the coordinates in which the fluid is at rest, comoving coordinates would be the coordinates in which the metric is isotropic, and that is the frame in which the fluid is at rest. Yeah? Okay. Now, what is the forward velocity in the comoving coordinates?
C squared and everything else is zero.
Sorry?
C squared as the zero component and everything else is zero.
Yeah, very good, only that C is equal to 1. So I can simply write it as 1, 0, 0, 0, of course, right? Or everything, for velocity, right, that describes a particle at rest or a fluid at rest, right? There are no velocity components. By the way, can you see my mouse on the screen? Yeah, okay.
Yes.
Okay, very good. It's not. So it's just a 1, 0, 0, 0, right? There are no, in a co-moving frame, there is no motion. So there is no velocity in each in any direction. So it just be a 1, 0, 0, 0. So if I want to write down the energy momentum tensor, T mu nu, in the form of a matrix, right, then it's going to be a P plus rho, U0, U0, that's just P plus rho, and G0, 0 is just a -1, so I'm just going to get the rho here, right? Now the first term, for all the other mu and nu which are not 0, 0, it's going to be a 0, so it's not going to contribute anything. And then for the ij component, I just get gij times p, right? One, and yeah, because the G10 is always going to be a 0. Gi0 is always going to be a 0. So the energy momentum tensor is going to take the form of a rho 0, 0, 0, and then 0, 0, 0, and then Gij times the pressure P. Now I can multiply that by G mu lambda, essentially raise one index. And that means that T mu nu with one index raise is just a diagonal of a minus rho P P P. Okay? From which we can take the trace, which is just T mu mu, it is just T, it is just minus rho plus 3P. So now we can take this result and plug it into Einstein's equation. R mu nu is equal 8 pi g, T mu nu minus 1/2 g mu nu t. If you remember when we derived Einstein's equation, this was one of the forms that we derived of this equation. Yeah? You agree that I'm not cheating? Okay, how many equations are written here? If you say that you agree that I'm not cheating, how many equations are written here?
16.
16, right. But in fact, we don't care about many of them, right? Because of this idea of isotropicity. So if we take the mu equal nu equal to 0, so the 0, 0 component, right? Then the 0, 0 component, we need to go back to this R0, 0, which is here. It's -3 a dot dot over a. -3 a dot dot over a is equal to 8 pi g. T0, 0 is just rho. Plus 1/2, because the G0, 0 is a -1, so a plus 1/2 times T, which is minus rho plus 3P. So when we open it up, this internal parenthesis, we end up with a -3 a dot dot over a is equal to 4 pi g times rho plus 3p. And then the mu nu equal ij, you write as rij equal 8 pi g, again, gijp, which we took from the definition of T mu nu here. Minus 1/2 gij t, which is minus rho plus 3p. So it's 8 pi g times 1/2 gij rho minus 1/2, we have here 3/2, right? So 1 minus 3/2 is minus 1/2 gijp, so it's 4 pi g, capital G, times gij times rho minus p. Now, of course, these are 9 equations. But because of isotropy, they are all dependent on each other. In fact, they're all the same equation because we don't care which direction we're looking at. So we can simply take the 1,1 equation, where we know that G11, which we derived, is just A squared divided by 1 minus KR squared. Right? And R11, on the left-hand side, we derived it previously. It's A dot dot plus 2 A dot squared plus 2K divided by 1 minus KR squared. So the 1 minus KR squared will be cancelled with this 1 minus KR squared here. And we still have this A squared, which is moved to the other side. So we end up with A dot dot over A plus 2 times A dot over A squared plus 2 times K over A squared is equal to 4 pi G times rho minus P. And the last thing we can do is to use this equation here to get rid of the second derivative. What did I do here back? What did I do here back? Let me see that.
Yeah, just divided by -3 and then put it
this
in
is
the
divided. Okay, this is just divided by -3, so we ended up with A dot dot over A is equal to minus 4 pi G over 3 rho plus 3p. So this equation is just the same as equation 41. And then I plug that back in here, and I ended up with A dot over A squared is equal 8 pi G over 3 rho minus K over A squared. So these two equations, 44 and 45, are equations that determine the evolution of this scale factor A, which evolve in time. Right? This is the second derivative, and this is the first derivative squared. Depending on the density, on the energy density, rho, pressure, P, and also this value of K, the curvature of the universe. Now, combined together, these are known as the Friedman equations, because they were first derived by Friedman. I think he's a Russian guy in the 1920s. And the total metric that we derived is called the Friedman-Robertson-Walker, or in short, it's called the FRW metric. So again, the FRW metric is the Friedman-Robertson-Walker metric. It's a metric that describes a universe which has a fully maximally symmetric spatial part. And so the metric would look like that. And the evolution of the scale factor, that the factor that multiplies all the spatial terms, is governed by these two equations, which are called Friedman equations, which we derive. All right.
Tough. Rho and P are time independent, right? So it's straightforward to solve it.
What?
Rho and P are time independent, right?
Well, we'll see. We'll see. Rho is the energy density of the universe, right? It changes, right? The density can change. It's actually not time independent.
Okay.
But we will solve it. Okay, I'm sorry for these technical problems that occurred. I've got no clue why they happen. As you know, this is the first time they happen to me. I don't know if rebooting the system will solve that or maybe changing the cable, but the cable does show that it's charging, so there is a connection. I will call some technical help to help me resolve it, and I hope it will be resolved by Sunday. If not, then we'll have to find some other way of continuing. Any further questions? Any questions? I hope that it was okay despite these technical problems that we had to face. Not so okay. It's less than ideal, but that's what we have right now. Okay, so I'll give you the next problem set today. It will be, I think, the one before last. Again, those of you who I do ask you to catch up with things. You know, if you ask for some extension in a few days, that's fine. But if you're, starting to run far behind, that's not good. I will not accept the problem sets if you come to me like one week or few days before the exam and tell me, oh, here is the last 5 problem sets which I didn't have time to do. Then I will not accept them. Don't play with that. I'm flexible as long as I'm seeing that you're working. Have a nice weekend, and hopefully any more technical problems. And